Okay, everyone, let us get started with today's lecture. Today is, I would say, one of the most interesting lectures of this boot camp, and it is very much practical. So let me start sharing my screen and let's start to understand this. Okay, so today we are going to understand how to build RL agents which can play video games. And we are first going to understand this topic from a historical perspective. And then slowly we are going to build our understanding to be able to build this RL agent by ourselves. So let us get started. So first of all, which type of video games are we talking about? So these are the type of video games we are talking about. I'm not sure how many of you have played such video games which uh, were not necessarily having the best of graphics, but they kind of looked like this. So I have definitely played these video games. These are also called as arcade games, actually. So you can see that the graphics quality is really poor. Today's video games are uh, have much more clarity and are much more realistic. But today we are going to learn how to play one such video game. Uh, so the history of video games has been that the first ever video game to be uh, built in an arcade was developed by Atari in the year 1972, which is around 53 years back. So it was a coin operated video game. You had to insert a coin and then play this game of Pong. And the concept was completely revolutionary at that time. You can actually check out Pong as I'm going along. In the game of Pong, what happens is that you have you have a paddle and then the opponent has a paddle. Maybe I can show you how this game plays out. So this is how the game of Pong actually looks like. So you can see here, let's say the ball moves around, and then your goal is to get the ball past the opponent. So basically, you can either move your paddle up and down, or you can not do anything and just keep the paddle the way it is. The concept was completely revolutionary at the time, and people really loved it. No one knew what was video games before, but then this was first installed in a in an arcade. Now, this was fine, but it was still not available for people at home because these arcade units were very big and they were installed in some kind of area which had a big space. So it was not available for people to be consumed at their houses. So then this was the case until microprocessors became available in the year 1975. So because microprocessors became available in 1975, Atari released the home version of Pong. It was a self-contained unit. You can just plug it into the TV and play. You can see how you can plug this into the TV. I'm showing this on the image on the left, and it was an instant hit. You can imagine why kids love playing these kind of video games. And this was exactly 50 years ago. So, and then this made home gaming completely mainstream. So this has been the history of video games, how they have evolved over the years. And then in 1977, the arcade video computer system was launched, and then it sold even more number of units. It sold 4 lakh units. So these video computer system or VCS, they had knobs which you can control. And then you can control the characters in the video games with the help of these small little knobs which you can see on the screen. But then, okay, fine. We brought the video games from an arcade or a big space level to homes, but then people are still not satisfied. We wanted to write codes to interact with the system autonomously. And then people ask this question that can we develop an AI which can actually play these video games? Can intelligent systems be developed like that? Uh, so after 40 years, that is in 2013, this idea was actually proven in this paper. It's a very famous paper. It gave rise to the birth of the field of deep reinforcement learning, and it was published by DeepMind. And then suddenly people realize that reinforcement learning is not just a classical theoretical framework which looks great on a piece of paper, but there are a lot of practical applications. And when you will see this in today's lecture, you will actually get this feeling that, okay, I have actually built something which is truly intelligent. That feeling I personally did not get when I used supervised or unsupervised machine learning algorithms, because you knew what you're doing. You're giving a lot of training data to the system and then the system is learning from it. But with reinforcement learning, it almost feels like you're developing a clone of a human who is intelligent. And that's what people realized after 2013. And you might have realized that this coincided with the boom in convolutional neural networks when AlexNet was developed around a similar time. So the boom of deep learning coincided with this paper coming out very nicely. And this was one of the main reasons why the field was reborn. Uh, I wouldn't be wrong in saying that if this paper would not have come out, RL would have been a dead field. People knew that, okay, it is promising, but no one had really seen any good applications coming out of it. So I'll just stop sharing my screen and load one more presentation. Okay, I hope you can see my screen. So after this, now we are going to understand how exactly did this transformation happen, and we are going to replicate this paper, playing Atari with deep reinforcement learning, in today's lecture. That is going to be our major objective of today's lecture. And we are going to do that in 4 or 5 parts. And I am deliberately going again through the basics of RL because some of you might need that revision before I directly jump onto the main concepts which were introduced in the Atari paper in 2013. So this, consider part one as a revision of all we have covered so far in a very simplistic term so that you can easily understand. In reinforcement learning, we have an agent environment interface. So typically you have an agent which receives a set of observations from the environment or states. And then based on these set of states, the agent performs an action according to a policy pi. And then after the agent performs the action, the agent receives a reward from the environment. And then again, it takes an action, receives another reward, and this process continues. So all the reinforcement learning problems are first modeled in the agent environment interface with states, actions, rewards, and policy which guides the behavior of the agent. Some examples that we looked at, classical examples: playing chess, a gazelle learning to run, then planning our breakfast. In all of these examples, there is a specific goal in the mind. So, for example, when I am playing chess, my goal is to win against my opponent. And at every state, which is a configuration of the chess pieces on my board, I'm going to select an action which is going to be aimed at reaching my goal. So we are not concerned about immediate rewards in all these examples, but the long-term goal is to win the game of chess. And this behavior, which action to choose for which state, that is guided by the policy. Same is the case for a gazelle learning to run. And when we are planning for our breakfast, we are doing a series of coordinated actions with the final goal of obtaining nourishment. That is the goal in the third case. In reinforcement learning problem, the agent needs to decide which action to take to maximize the reward. This is what makes it different from supervised and unsupervised learning type of problems, where you are given a set of training data and then you're trying to either extrapolate or generalize to unseen data, or you're trying to find a pattern or clusters. Here, that's not the goal. Some cases you're not even given the data, you're obtaining the data by experiencing the environment by yourself. And then you are learning to navigate inside the environment with the goal of maximizing the rewards at the end of the episode. How is this decision made? We'll take an example. Let's say you're the coach of an IPL team, and any sport for that matter, and your goal is to maximize the amount of matches your team manages to win out of 14 matches. Now, this is the agent environment interface. In this case, the observations or the states are the history of all the previous matches, performances of each player, etc. And then after every observation, you are taking an action, which is, what is my team? What are the 11 best players? And then you are getting a reward. If the match is won, reward is +1. If the match is lost, then the reward is 0. Now, the question we want to ask is, do we take our actions uh, just based on the immediate rewards? So one simple policy is that I'll look at players who performed well in a match. And if a player had a very bad match, I will remove that player from the next match. This is a very simple policy, but as a coach, it would be a much better strategy to bet on the long-term value of the player, which means that what is the uh, how likely is this player to score well or play well in most of the 14 matches that are going to be played in the tournament. So I'm looking at the long-term desirability of this player, not on the short-term desirability. So if you look at the player roster, you can build two columns: immediate rewards based on how they performed in the match, and long-term value based on what they have done in the past, what you think of them, what is your intuition, depending on the scenario. And then usually decisions are made based on the long-term value, not with respect to the immediate rewards. This is exactly what is done in reinforcement learning. And in fact, this long-term desirability is expressed in a variable which is called as value of a state. Value of a state means that starting from that state till the end of the episode, what is the expected return which the agent will receive? And how do you calculate this expected return? You add all the immediate rewards from that state to the end of the episode. With one small change, you discount the rewards, you add a factor of gamma. So you say that current rewards are more valuable than the rewards which I receive later. So the equation is going to be R1 plus gamma R2 plus gamma square R3 dot 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 till the end of the episode. Now the question is, okay, this is fine, but where do we store these long-term returns? These long-term returns are also called as Q value. The definition of the Q value, which we looked at in the last lecture, is the expected return for an agent starting from a state and taking an action. And then what we do is we store these long-term returns for all the possible states and the actions. And then for every state, we look at, okay, let me look at all these actions. There are 4 actions. action number 2 has the maximum Q value. So I'm going to pick that action for this state. So looking back at our example, for the same player rooster, which are the states in this case, I can have different Q values. Player A has a high Q value, player B has low, player C has high, etc. And then depending on these values, I will choose the 11 players which have the maximum Q value. And this is how the decisions are made. For all the states, you construct this table with two columns. On the left hand side, you write down all the states. On the right hand side, you write down all the values of the expected return, starting from that state and taking some action. So ideally, you would have two columns here, states and actions, not just states. Okay, now the question is that this is fine. Even in the last lecture, we looked at how to build this Q value table. So in the last lecture, we looked at three methods to build this Q value table. And the three methods were dynamic programming, Monte Carlo methods, and temporal difference methods. Dynamic programming is a technique which requires a complete model of the environment. It requires the probability of transitioning from a current state to the next state. In most of the RL problems, that probability is not available to us. If I am playing chess, I don't know the probabilities of different moves, right? So it's something which started the field, but it's never used in practice. Monte Carlo methods, on the other hand, do not require any sort of model of the environment. What we do in Monte Carlo methods is that we uh, simulate a bunch of episodes. And then what we do is we understand what kind of rewards the agent is receiving for all the episodes, and then take the average of all of them to build the Q value table. But then the problem in Monte Carlo methods is that to make one single update, we have to wait till the end of the episode. Otherwise, we cannot make that update. So then people developed this method called temporal difference learning, in which we look at the next state value, the value of the next state to update the value of the current state. So it becomes a much faster algorithm. And in the last class, we had taken the example of us traveling from our office to our home. And if there is a small traffic jam in the middle, I want to update my estimate immediately. I don't want to wait till I reach home and then update my estimate. That's exactly what temporal difference methods do. And then one of the most popular algorithms within temporal difference methods is called Q-learning, which I'll again revise in today's lecture. Now, estimation of these Q values till 1990s to 2000s, people used very long tables to store Q values, something like this, very, very long. Imagine that you're playing a game of chess. Now a game of chess has 10 raised to 44 states, huge number of states, right? And for each state, there are dozens of possible action, right? If let's say look at this chess configuration on the screen, and if you are playing white, there are many actions you can take from this state, maybe 20, 30. So you multiply that states and actions and see how many state action pairs you would have to list down in the Q table. It would take billions of years to store all the values in a table. So even though the storing all methods, storing all Q values in a table and then updating that using the Q learning algorithm looks like a robust framework, it's not at all practical because you need to have a lot of memory, which is completely not possible and it's impractical. So for a very long time, we were actually stuck in this phase that people didn't know how to solve these problems, which had a lot of states. We could solve simple problems like tic-tac-toe, which had maybe a definite set of states, but real life problems, actual complex problems have a lot of states. And in the last lecture, I had asked this question to all of you towards the end, that we cannot store these long tables. So what is the solution? And then the question is that now, can we store Q values for only some states and approximate to others? For example, let's say what if we use only 10,000 states for training and then use the trained model to predict the values of other states? So this problem and this solution sounds very, very familiar, right? In fact, this is the core of uh, all machine learning frameworks. This is why the field of machine learning was introduced, that you have a limited set of data, you analyze that data and you build a model, and then you use that model to generalize on unseen data. That's what we want in this case. We want to just look at through a narrow lens. We want to look at a fraction of the states. We want to understand something and then we want to generalize the Q value to all the other states in the environment. So this is exactly what function approximation methods do. Typically, they look at input-output pairs, they form a line or they form a function, and then you throw away the data, but you use the function to generalize to all other states which your agent has not seen before. So the question that we are asking is that can we uh, use a neural network to firstly train the neural network on a bunch of states and Q values. So if you look at the table on the right hand side of this image, we have two columns. The first column is the state and the second column is the Q value for that specific state. Now what I will do is I will uh, train this neural network so that for each of this input, I match the output, which is the Q value. So I'll call my neural network as a network which predicts the Q values. And then I will definitely need some states for this training data. Then what I will do is I will throw away this input output pairs and I will just use this neural network to make all my predictions. So this is something which will theoretically solve that problem of having to store 10 raised to 44 states in a long table, because here all you need to do is provide this input output pairs, train the neural network, and then the neural network will predict uh, the output. For each state action pair, the neural network will predict the Q value for that state action pair. Now, if I was a scientist 30 years back when people started discussing about it, I would not have believed in this. The main reason I would not have believed in this is in traditional machine learning problems, the input output pairs of data is pretty well known. You have an image of a tumor, you know whether it's benign or malignant. But here, how will you construct the training data? You know these states, for sure you know the states, but you do not know the Q values for these states a priori. So the problem is that you do not know the target variable or the output variable at all. And this complicates the training even more, because when you think about it, it's not a problem where you're given inputs and outputs and then you're training a neural network. But these outputs are also not given to me, because Q values, remember, it depends on the expected return the agent receives after following an action A from a specific state. How will you know that expected return before you start experiencing the environment? How can a neural network generalize on unseen data on such problems which require complex reasoning? So I would have been a skeptic of this, to be honest. But then one major change happened for the benefit of our society. Uh, until 1992, there was this person called Gerald Tassaro at IBM, and he developed a very interesting algorithm called TD backgammon. TD stands for temporal difference, where he used reinforcement learning to play the backgammon game. And the agent was so good that humans were amazed by it. It could perform moves which humans could not anticipate what it's going to perform. And then this was a very big deal because deep learning was not even developed. Remember, deep learning as a field became popular in 2010. So in the 90s, people were still skeptical about neural networks as it is. And then this person used neural networks, which people had given up hope on, and used neural networks to train the Q value predictor, and then solve this problem of backgammon, which also has a huge number of states. So this was the first pivotal moment in which started the whole modern reinforcement learning field. And by 2013, we had good enough computing power to have deep neural networks, and that's when this paper came out. So you can see in the abstract of this paper, they actually mention that we present the first deep learning model, which means that they have used a neural network to predict the Q values for every state. That's all it says. So reinforcement learning papers, when you first look at it, you might get scared to see, okay, what is all this? But at the heart of it, the theory is very, very simple, which I'm just going to explain in today's lecture. So this is what we are looking at. This is the brief history. We are going to look at function approximation methods from today onwards. Up until now, we have been focused on tabular methods, but they have their own set of constraints. They cannot be applied in practical settings. So we have to use function approximation methods to approximate the Q values for all these states. So let us understand now how that is done exactly. And in part three, we are going to now focus on how do we learn to play the game of Pong with reinforcement learning. And as we go along, I'm going to ask a bunch of questions to you so that I want to just probe your understanding. I 2 weeks back, I took a lecture on this in our office, and the intention was to understand the points in the teaching which uh, are the pain points for learners. So I am aware of these points now, but it will be great to have that feedback as well. Okay, so let us look at the uh, Atari game environment of Pong. If you have not seen it before, if you have joined late, this is the game of Pong where you are the red and the yellow is the computer, and your aim is to get this orange ball past the paddle. So that's your goal. So we are going to now look at exactly how that works. But before we look at any reinforcement learning problem, it is important to understand what is the agent environment interface here. So let's understand that. First, the question is, what are the states here? Can anyone write down in the chat? What do you think are the states in this example? So what are the observations which our agent is receiving from the environment before the agent goes ahead and takes any action? So Animesh says that it's different positions of the paddles. Shishir says that position of the ball, position of the paddle and the ball. Naveen says entire screen. So all of you are kind of similar, and Naveen's answer is actually correct. The state is a single game frame which has 210 by 160 pixels in a single frame. So instead of just capturing the location of the paddle, the location of the ball, which is what we want to do finally, but we want to give this entire image to our agent as the observation. So this is the state which our agent sees, and it is of course pixelated, as is done in any computer vision task. Before you feed any state, uh, a computer cannot understand image like we do, but it understands images in terms of pixels and the value of the pixels which depend on colors. So here every pixel has three channels: red, green, and blue. So the total number of values will be 210 by 160 by 3 in a single frame, which go as a set of observations to our agent. So this is the state. Actions are simple. There are only three actions. We can either move the paddle up, we can move the paddle down, or we can choose not to do anything. So there are three actions which our agent can choose uh, in this environment. And then the rewards are +1 if the agent successfully hits the ball past the opponent's paddle. The reward is -1 if the opponent hits the ball past our paddle. And then for all other frames, like the one which I'm showing on the screen right now, the reward is 0. So this is how I construct my state, my actions, and my rewards. If you have managed to reach till this point, most of the complexities of the RL training process is over. And just a small digress here, if we imagine large language models, states, actions, and rewards are not very clear, but it's very interesting to think about LLMs as an agent, and then what are states, actions, and rewards. I will definitely cover that in one of the later lectures, but I want you to start thinking about that from now itself. Okay, so now let's move ahead. So this is how our agent environment interface looks like. Our states are the frames of the game, and then the pixel values, RGB values for all the pixels. Actions are only three, either going up, going down, or not doing anything. And there are three different rewards: +1 for success, -1 for failure, and if I don't do anything, then my reward is 0. Okay, so now we have defined the agent environment interface, but how do we find an optimal policy? Let's understand. First question is that can we use dynamic programming? Uh, you can mention in the chat if we can use dynamic programming in this application. So Himanshu says no. Yeah, everyone says no. Monidipa says yes. Padma says yes. Shishir says no. No is the correct answer. The reason is that if you look at this agent environment interface, do you know the probability of transitioning from one state S to the next state S dash? The probability is not known to us, right? Because it's not a simple environment, it's a pretty complex environment. So if you don't know the probability, the transition probabilities, the dynamic programming is completely ruled out of the equation. You cannot use it. The second approach to find a policy can be using Monte Carlo methods. What do you think? Can we use Monte Carlo methods for this approach? So Naveen says yes, yes, yes. So theoretically speaking, Monte Carlo methods can be definitely used for this approach. But again, the problem with Monte Carlo methods is that if you imagine one episode in while playing the game of Pong, Monte Carlo method will only update your Q values after the entire episode is over. So it will take a very long time to run, and it will not leverage the individual rewards which I am receiving in the process. So Monte Carlo methods, although can be used as a theoretical algorithm and it will work, but the conversions will not be straightforward and it will take a long time to converge because uh, we are not we are waiting till the end of the episode to make one single update. So there is a lot of information in that whole episode which we are missing. Now, the third method that leaves us with is temporal difference methods. And in temporal difference methods, which we looked at in the last class, we are going to use the method of Q learning for this problem. Now, let us use Q learning for this task. And we are going to understand how exactly is Q learning going to be used. So, because the total number of states here turn out to be 10 raised to 70,802, huge number of states, right? Because the number of, if you look at one single frame, it has 210 into 160 into 3. And then all of these uh, single pixels can take any values from 0 to 255. So it's a big state space that we are dealing with. So we cannot use tabular methods. Tabular methods are ruled out of the equation for this problem. So then the next question is that can we use function approximation methods? More specifically, can we use neural networks to represent Q values? It again is going to bring us back to the question of input-output pairs. The first question I would have as a research scientist working on this problem is, I do not know what is the output. So how can I use a neural network for estimating the Q values? So we are going to understand that how exactly are Q values used for this process. So this brings us to part 3A, which is understanding the algorithm behind uh, these deep Q networks. It's called deep Q networks because we are using a neural network uh, to predict the Q values. So let's look at conventional conventional Q learning algorithm, and I just want to take a small detour and maybe check if I can write it down for you to understand. Okay, so in the conventional Q learning algorithm, what happens is that you write down this equation Q of S comma A, which is the uh, action value function, is equal to Q of S comma A, which is the previous value, plus alpha, which is the step size parameter, uh, target minus Q of S comma A. Now, for Monte Carlo methods, this target is the expected return, which is G, but that we only receive till the end of the episode. So for Q learning, this target is given by R, which is the immediate reward, plus gamma times Q of S dash comma A dash, which is the Q value of the next state and action. But we make a small change here. So I'll rub this again. We take maximum over all the possible actions Q of S dash comma A dash. So essentially what we are trying to do in this whole process is that just forget about this target for a moment. Forget about it. Uh, what we are trying to do is we are trying to move this Q of S comma A towards this target. If this target is same as Q of S comma A, our update is this is going to be 0 because this Q of S comma A minus Q of S comma A is going to be 0. So the original value is not going to get affected. But now imagine a case where our target is very high, which means that this difference is very high. So our Q of S comma A will increase by a high amount. So intuitively, what we are doing is that we are moving this Q of S comma A closer to the target, but by a small amount, which is given by this alpha, which is the step size parameter, which goes between 0 and 1. So this is the step size parameter. So now, does this give you a hint of what would be the output for our neural network? This whole discussion is intended to give you an hint as to what my output will be looking as. So basically, what if I use this target itself as my output? Because I do not have my output for each input pair, but I know the target, right? I know this for all the input, for all the states and actions, I can estimate this R plus gamma max of A dash Q of S dash comma A dash. And what if I use this itself as the target of my neural network? And then this is exactly what happens in the modified Q-learning algorithm. Everything stays the same. But okay, first let us look at the traditional Q-learning algorithm. You start with an empty table for Q of S comma A. Okay. Then you obtain the states, actions, and rewards from the environment using the epsilon greedy policy. You obtain A dash, not using epsilon greedy policy, but using the greedy policy because we have a maximum over here. And then you make a Bellman update using this equation, which is exactly same as what I have written here. The only difference is this should have a minus Q of S comma A, which I forgot to add here. So you make a Bellman update and you keep on doing this until Q of S comma A doesn't change by a large amount. This is the traditional Q learning algorithm, uh, which is used to make updates. Now, what happens in the modified Q learning algorithm is step 1 and step 2 stay exactly the same, but now we do not have a table to make the Bellman update. Instead, we have to calculate the loss. And to calculate the loss, we use Q of S comma A as the input. And then we use this as the output. So for each state and action, the loss is calculated by how does my Q of S comma A differ from this target, which is exactly the same target which I have mentioned over here. So I try to optimize the weights of my neural network in such a way that this loss is minimized. And this comes about from this exact same intuition. Let me repeat that again. So here what we are essentially trying to do is that we are trying to move Q of S comma A towards the target. Why we are doing that? Take a simple example. If the target minus Q of S comma A is very, very small, Q of S comma A will not change that much because this value will be less. But imagine a case where, let's take an example. Imagine a case where uh, let's take a case of Q of S comma A is equal to 100 and let's say target is equal to, in first case, 105. So what will be the updated value? 100 plus, say gamma is equal to 0.1 or alpha is equal to 0.1. 100 plus 0.1 into 105 minus 100, which is equal to 100.5. But if the target is, let's say, now we take a second case of target is equal to 200, my Bellman update looks like this, which is equal to 110. So I have moved from the original Q value towards my target. Okay, so this is exactly what we are doing. We are not exactly moving to the target, but we are multiplying this by a value of 0.1. And that's why here also we are doing the same thing. We want to minimize this loss because we want to move this Q of S comma A as close as possible towards the target, which is R plus gamma maximum of Q of S dash comma A dash. This is exactly how we are going to modify the original Q learning algorithm towards a Q learning algorithm which includes a neural network. So Pramod asks a question that how is A dash identified in this? That is a very good question. How is A dash identified in this? Because uh, you do not. So let me take an example. to answer that question. Let's say we have a neural network which takes in S comma A as the input, and it predicts Q of S comma A as the output. Now, the question is, how do we calculate loss for this input, right? How we calculate loss is, we know the output which is predicted by our neural network. So let's try to calculate the target. To calculate the target, you will take the same neural network, but you will pass on the next state to this neural network. Okay, and then you will get the values of q of s dash comma a dash. So you will get a lot of values. Let's say we have q of s dash comma a1, q of s dash comma a2, etc. You will choose the q here which has the maximum value, and that will become your target. That is how you will estimate the target. We will look at this very closely. Don't get confused at the moment. For now, I just want you to understand how the original Q-learning algorithm is modified, because we are moving from a tabular method to a function approximation method. So here you might have noticed something strange. The target for our neural network is related to our neural network itself, right? This is something which never happens. So here you can see the target, which is q of s dash comma a dash, is related to our neural network. I'm not sure you have seen any example like this in supervised or unsupervised learning, because the target is usually completely separate. It's not dependent on the input itself. Now, this is something we never do in these type of learning problems, where the target is itself dependent on the neural network. And this is just something where I have drawn a schematic for you to understand this whole process better. Forget about what's going on inside this box. Just imagine that there is a state and action coming as an input from this left-hand side, and then we are predicting the Q values. Now, look at this, how the loss is calculated. We have one input to the loss, which is the Q values of our current observations. Now you use the same neural network and you calculate the Q values for the next observation. You multiply that with gamma and you add the reward. Okay, and then you subtract it, calculate the loss, and apply gradient descent. This is how we perform the gradient descent operation when we replace tabular methods of representing Q values with function approximation methods. In conventional supervised learning, this whole thing is replaced by just one single output variable. But here we do not know our output, so we have to use the same neural network to predict the output. So we estimate Q values for next observations, calculate the maximum, multiply that by gamma, and then add the reward, calculate the loss. And then we continue this stochastic gradient descent algorithm and keep on modifying our weight parameters. This is how the Q learning process or the deep Q neural network works. Now, up until this was fine. Imagine that you are the first one who is trying to implement this paper for Atari games. The moment you implement this algorithm, you would realize that it does not work at all. There are big problems and the network doesn't converge. It's not working. That's what Google DeepMind also faced. And to resolve this, we are going to look at the 4 acts. This is how I have named it, of deep Q networks, which were the major contributions in this paper. And this is used everywhere in modern reinforcement learning. So let us try our best to understand these 4 acts. The first act is interaction with the environment. Now, this is something which we have already discussed in the last lecture. Uh, if you have a policy where you are always performing a greedy action, let's say you have this queue network, right? You have, let's say, this queue network, okay, which is predicting the queue values. Now, let's say your model is trained and is ready for the agent to use to play the Atari game. If you always, if in the training process, if you always use a greedy policy, which means that if you always select the queue value which has the maximum value, or if you always select the action which has the maximum queue value, you will be simply exploiting the information. But it might happen that you are missing out on certain actions because of your greedy policy. That is why people use an epsilon greedy policy where the exploitation is balanced with the exploration. So this is actually something you see here also. It's not very new. Remember, here in step number 2, I have written epsilon greedy policy, and here also I have not mentioned, but this is how this SAR is obtained by using an epsilon greedy policy. The same thing works in the modified Q learning algorithm also. When you interact with the environment and obtain the next states and the next rewards, you don't just look at the action which has the maximum Q value, but you, with a probability of zero point 0.1 or 0.05, you take a random action once in a while. So this is the first act, which is a balance between exploration and exploitation. And here also what people do is that initial part of the training, the agent will be very raw. The agent will have no knowledge of the environment. So it makes sense to have uh, epsilon value to be a bit high. But then once our agent starts to become better and better, then we don't need it to explore very much, right? Because we know our agent is getting better. So usually people use an epsilon decay rate where the epsilon is very high at the start and then it slowly decays as your training progresses. So this is the first thing they did. It was not completely novel, I agree. It was already established in the past, in the 1970s, 80s. The act number 2 is truly novel. It's called as replay buffer, and there is a very logical reason as to uh, why does the replay buffer exist. So one of the fundamental requirements for stochastic gradient descent optimization is that the training data is independent. You look at any example, let's say we look at brain tumor image classification or insurance price prediction. Every single sample does not depend on the other sample, right? They don't have any correlation because the training data is randomly sampled from the underlying data set. But then what happens in this case is, imagine you're playing a game of Pong. Let's take an example here itself. Let's look at this. Now, within one single game, look at the current frame and the next frame. The next frame is dependent on the previous frame. So the states are correlated with each other. Shravan is asking because of, no, this is not related to Markov property. I will come to that later. Here, what we are saying is that the states are dependent on or correlated with each other. Let me actually draw a diagram for you to understand. Let's say this is one state where the computer's paddle is here and our paddle is here and the ball is somewhere in the middle. And look at the next state where the computer's paddle moves a little bit up, our paddle moves down, and the ball moves to the right. So this is, let's say, state number 100 and this is state number 101. So these two states are not independent because they are sampled from the same episode. They are completely dependent on each other, right? So it does not satisfy this IID criteria, which is a major problem. And that's one of the reasons why they were not getting good results. And one simple way of doing that is, why don't we have a replay buffer where let's say whenever an episode is complete, or whenever we get a state or observation from an environment, we store the data in the replay buffer. Then we again play the game, again store the data, again play the game, again store the data. And then when we are training our agent, we randomly sample from this replay buffer. So instead of using steps or states which are correlated, because this replay buffer probably contains information from 100 games, and let's say you're sampling a set of 100 images, one image can be from episode 1, the second image can be from episode 100, third image can be from episode 50. Now these images will not be having any sort of correlation with each other. So replay buffer is a pretty simple concept. Every time you take an action and you get an observation, you go ahead and store it. And then every time again you take an action, go ahead and store it in the replay buffer. So this is the second act, which is the existence of a replay buffer. Now it sounds very intuitive, right? But no one had thought about this before 2013. Act number 3 is also very important, which is called as target network. Now, what happens is that you would have noticed that we are using the same neural network to calculate the Q values of the current state and the next state, and the next state value is used to calculate the target. So this makes them very similar and hard for neural networks to distinguish. And this is like, it's like a mice trying to bite its own tail, because the moment you make any change in your queue, in your neural network, then your targets will also change. And the moment you make any change in the targets, your network will also change. So because of that huge sensitivity between the uh, neural network which we are going to train and the output, and the huge dependency between them, it creates a lot of problems during training. And because of that, what people do is that usually the only weights which are updated is they use two different networks. First of all, they use one network for estimating the Q values for the current observations, and one network for estimating the Q values for the next observations. Now you use stochastic gradient descent to update the weight parameters only in this first neural network. You don't update. Basically, you freeze this target network. But after every 50 or 100 time steps, you transfer the weights of the current this network to this network so that they are matched. So let's say you start from step number 0. Okay. Now both will be initialized with same weights. Then the first neural network will change. The weights will keep on getting updated. But then the target network will stay the same. Only after a set of, let's say, 1,000 steps, both networks will again become same. Then again, you start modifying the first network, the weights will be updated. Then again, it will be transferred. Then both will be same. Then this process will continue. What this does is that when we are calculating our loss function, the target which the loss function sees is not the exact same network as the network which we are trying to optimize, because the network has been frozen since a long time. So this actually works a lot. And then, so these two, act number 2 and act number 3 is one of the main innovations which they brought about in this paper. And then finally, as Shravan mentioned, we discussed the Markov property also. The game of Pong does not satisfy Markov property. Remember, we had discussed that a state signal only satisfies Markov property if the entire dynamics depend on that state signal. We don't have to look at the past. Now, if I ask you this question, uh, you look at this frame where the ball is here and the paddles are here. Can you tell me what is happening here? Is this the complete information? No, because the ball can either be moving here or here. So just from the information of the state, this is not enough to predict the dynamics. Usually you need information from the past in the game of Pong to predict the future. And since the state signal does not satisfy Markov property, our Bellman equation will not work. So what people do is that they use a very simple trick. They maintain several observations from the past and then use them as a state. In the case of Atari, they do something like this, where they use frame stacking. You don't use a single frame as the state, but you stack four frames together and you pass that stack as an input to your network for training. So this is something which is used to negate the state signal not satisfying the Markov property. And then this is the final DQN algorithm. It looks a little bit like a lot of text I have added on the slide, but let's understand this. So the first step is we initialize parameters for uh, our Q network and the target network, which is denoted by Q hat, with random weights. Initially, epsilon value is pretty high. You can see here, epsilon value is 1. And then the replay buffer is currently empty. Now what we do is, with probability epsilon, we select a random action. Otherwise, we select an action which has the maximum Q value. This is our epsilon greedy policy, which is important to balance exploration and exploitation. Next, we execute the action in the emulator, which is the Pong game, and then observe the reward and the next state. Okay. Now, the important thing here is that we don't just store the next state in the replay buffer, but we store the state, the action, the reward, and the next state. Uh, why do you think this is the case? Why do we store all this information in the replay buffer? Why don't just store S dash and R, or just S dash for that matter? The main reason why we store all of this is that, remember, we are sampling randomly from the replay buffer later. So when you sample, you need to be able to calculate the loss properly. So to calculate the loss, you need to have S, you need to have A, you need to have R, and then you need to have S dash. Okay, so this is step 4. In step 5, we randomly sample a mini batch of transitions. This is what negates the correlation of the steps, and that is how our data satisfies the IID property. So this is act number 2. And then for every transition in the buffer, we calculate this target, which is R plus gamma times maximum of this network, which is the target network. Then we calculate the loss, and then we only update Q of S comma A. You can see here using the stochastic gradient descent algorithm by minimizing the loss. And then every n steps, we copy the weights from Q to Q hat and then repeat until converged. So I'll just pause on this slide for a few seconds for you to internalize the algorithm and go through it. There are totally 10 steps. So what is the meaning of IID property? So whenever we sample data from the training data or the samples of training data should not be dependent on each other. We should ideally have data which is independent of each other. And that is the whole reason why we have the replay buffer in the first place, and why we randomly sample a batch from the replay buffer, because we don't want the uh, states to be dependent on each other. So another question is that, is Q hat for target network? So yes, Q hat is for target network, and every n steps we sync the weights from the Q network and to the target network. That is how we are going to sync both the networks in this whole process. So overall, it's very similar to our modified queue algorithm, but the only thing we are doing is we are adding a replay buffer and we are adding a target network here. Okay, so now what we can do is we can actually now go ahead and implement this DQN in practice. While I am doing this, I want you to go ahead and look at this repo, and you can clone this repo, and there is a folder called deep Q learning. So I want you to clone this so that when we get to the implementation stage, you are ready uh, with the code files on your local editor. Okay, so we'll understand all the questions which have been asked in the chat, because while we are implementing our model in practice, we'll be revising all these concepts anyways. So let's go ahead and start it. The first element is the DQN model. And this is our neural network. So you might have questions. What is the architecture of this neural network? How many layers it has, etc. So you might have guessed that we need a convolution layer because our observations are images. So we definitely need a convolution layer, and we need a linear layer also. So this is how the network looks like. As I mentioned before, the input is uh, this observation. It's actually a stack of observations where k equal to 4, but for simplicity, I have just uh, used one single screen, or one single frame as an input. Then you go through 1, 2, and 3 convolution layers. And then the final flattened layers is connected to one fully connected layer, and finally the output. You can see the output is given by q of s comma a0, q of s comma a1, q of s comma a2, dot dot dot, q of s comma an. So overall, we have three actions, right? So we will have three neurons here in the output layer, but the rest of the things will remain the same. And then let's have a look at the code for this, which is the same code which I have used in the GitHub repo, which I have asked you to clone. So let's look at the code in detail. So this is the code which we have used. So here you can see that the first layer is the convolutional layer. The second is also convolutional. Third is also convolution. Then we have these ReLU activation functions at all places. And then finally we flatten the output. And then the flattened layer is then fed to this linear layer. And then this is the output layer finally, where you have these n actions as the number of neurons in the output layer. So, and then what you do is that you first pass it through the convolutional layer, and then you pass it through the fully connected layer. So whatever I had shown in the diagram over here, this is basically an exactly same code replica. So I'm just going to share this with you so that you can just go through this in detail. So the entire code is actually not very big, and I'm going to explain all the key aspects, but have a look at this document, and first we'll focus on the first element, which is the BQN model. Okay, so this is the first element. Now let's go ahead to the next element, which is performing a step in the environment. Now, remember from the way we had given the 10 steps, how do I perform the step in the environment becomes very crucial, because mm, the action which I take to uh, the action which I take at each step should follow the epsilon greedy policy. So sometimes randomly it should choose an action, and sometimes it should actually look at the network and find the maximum value. So let's see how that is done. So element 2, we are looking at code 1 first, which is basically how the action is chosen. So this is how the code looks like. You can see here, if np.random is less than epsilon, it will just randomly sample an action from the action space. We had looked at this in the first and second lecture, where we had seen that the gymnasium environment has this variable called action space where we can sample from. This is exactly the same. But if np.random is greater than epsilon, what we do is we first pass the state, we pass this state to our neural network, and then we calculate the maximum of this and then select that as an action. This piece of code is what is act number one, which is epsilon greedy policy. So with a small probability, we take a random action, and rest of the times we use our neural network, and using the neural network, we calculate the action which has the maximum Q value. So this is how we perform the step in the environment. Now we'll look at this. Here also, you will see some familiarities with the uh, gym environment code, which we had seen in the first and second lectures. So here, just focus on this first line. See here, we are writing self.env.step. Env.step was something we need in the gym environment, and we have to pass an action to it. So this is the same action which was chosen here. And once this action is passed, we get the new state from our Pong game. We get the reward. We get two flags, whether the game is done, whether the game is truncated. And then this is where we append this whole experience to our buffer. So this is where we are building our replay buffer, where in the replay buffer, remember I told you that we had to update S, A, R, and S dash, which is exactly what we do. S, A, R, and S dash. That is updated in the replay buffer. And then finally, what we do is we convert all of these variables into the tensor representation. So here, what we do is you can see the states we have converted to tensors, actions we have converted to tensors, rewards we have converted to tensors, and the new states also we have converted to tensors. So basically, up until now, we are storing in the replay buffer uh, the states, we are storing the actions, we are storing the rewards, and we are storing the next states as well. Now what we are going to do is we are going to define the loss function. And this is one of the critical piece of this entire puzzle. How do I define the loss function? So first, to define the loss function, the action values of the current states are calculated. Let us look at what the loss function is. So the loss function is q of s comma a minus target the whole square. So to calculate the loss, we first need to calculate q of s comma a. So how is q of s comma a calculated? Q of s comma a is calculated using this approach. So let's say we have uh, a certain number of states as an input, and these states are randomly sampled from our replay buffer. We pass this to our neural network, and we get this table, where you can see that I have 32 rows because the batch size of my images is 32. And for every image which I pass to my neural network, I get four possible values: q of s comma a1, q of s comma a2, q of s comma a3, and q of s comma a4. And I also know what is the action taken. This is according to the epsilon greedy policy. So I have marked this in green. So 3 corresponds to this last one, 1 corresponds to second, 2 corresponds to this, and 0 corresponds to the first element, and 3 corresponds to this last. So these are the selected Q values which we need to calculate the loss, especially the first term, which is Q of S comma A. Now let us look at the code snippet for this, which is the first one, code number 1. So in code number 1, what we are doing is this. uh, we are simply, this one single line actually summarizes it. Uh, yes, this line summarizes it. So whatever I have written in the diagram, where you gather all the actions and then you uh, take out the numbers which have the entries uh, over here, that has been written in a code format in this file. And then after this is done, we have to remember calculate the second part of the loss function. And the second part of the loss function is done by calculating this, which is exactly the same as the first part. The only difference is that here the actions taken are the maximum. Let's go back again so that you can refer to the loss function here. Here the in the target, a dash is calculated by taking maximum. It's not according to the epsilon greedy policy. It's taken according to the greedy policy. So that's why we have this action taken, which is maximum. And the code block for this will have a max somewhere, which let's see. So this is how it looks like. You can see here that we have doing a dot max here and then storing it as the next state values. Now we are perfectly ready to calculate the loss function, and it's going to be a simple loop to calculate the loss function. Let's see how that is done. So the loss function is given by this. So have a look at this very closely. We are doing a mean square error between these two terms. First is the state action values, which is q of s comma a. And second is the target, which is q of s dash comma a dash, which is this, into gamma, which is this, plus the reward. Okay, and then we calculate the mean square error loss. So you can see how what we have done before comes together very nicely in the loss function. Now the last important piece of code that we have is the training loop. So let us try to understand this training loop in detail. Okay, so this is the training loop which we have, uh, where what you can see is, uh, let's go from the last block to the first block. Here we are sampling from the buffer batch size, calculating the loss, and then performing a step in the environment by calculating the by doing a round of back propagation, and then we take a step in the environment using stochastic gradient descent. This is what is happening here. Here what is happening is, if length buffer is less than replay size, then continue. So basically what this is doing is, we are not going to start any kind of training process until 10,000 observations have been uploaded into the replay buffer. So initially when I am playing my agent, I am just playing a lot of game of Pongs, let's say 1, 2, 3, 4, up to 10,000 games of Pongs. And then I update all those, or maybe I play less games of Pongs because I have to update only 10,000 observations. So if in a single game I have 40 observations, then maybe I end up playing 2,500 games. Only after these 2,500 games are played, I actually start training my AI agent. I start training my reinforcement learning agent, which is what is explained in this part of the code. And then you can see here we have agent.playStep, and playStep was mentioned here. So an action is taken in the environment. So this training loop continues. These are the series of important code blocks that are there to run the code. The rest of it is not very important for us to understand. And I believe that with this information, you will be able to understand the entire code which I have updated in the GitHub repository. So now what I'm going to do is I am going to go ahead and uh, run this. So let me know if you have cloned the GitHub repo. Okay, so let's get started. So now what we are going to do is that here, when you clone the repo, you will see that there are two files. One is dqn underscore play.py and second is dqn underscore pong.py. So we are interested in this dqn underscore pong.py and we have to run this file. It depends on, it uses two dependencies, which is in the library folder dqn underscore model. This is where our model is written, which I have explained this to you. And the second are wrappers. So all we have to do is we have to go here and run it. So here you will see all these different elements which I have told you. For example, this is the play step. This is where we are appending in the buffer. This is where the elements are converted to tensors. This is where the loss is calculated. And then finally we have the training loop. Okay, so the question is that since we both store S and S dash, why we completely randomize selection? So see, every observation in the buffer contains S, A, R, and S dash. So when we randomly sample from the buffer, we randomly sample multiple observations so that the states don't have correlations with each other. But within one observation, we still have S, A, R, and S dash. So that still exists. So now let's see. I'm just going to go here and say Python dqn underscore pong.py. No such file. Okay, so now I have again given the command Python. I just changed the directory I'm working in, and let's see. Hopefully, it should start the training process. So let me just keep it down. Okay, so it starts from this point. So you can see that first it has loaded the network, and then after some time you can see that the training process starts. Now on my laptop I'm using a MacBook which has 8 GB of RAM, and it takes around 7 to 8 hours or slightly more than that to complete the training process. So while this continues, I'll show this to you in a while. I'll just show the output that we get. So once you are done with this, what you can do is that you can run the TensorFlow by using this command, tensorboard dash dash log directory equal to runs. And then you will see the TensorBoard graphs like this. So this is what I got for the rewards. So let me just zoom in. So you can see that initially my rewards are very low, and then slowly the rewards start to increase. And then these rewards are calculated over 21 games. So a reward of 0 means that I'm not winning any of the 21 games. And you can see that I reach a point where I have become very capable to win a lot of games out of 21. And this is what I told you at the beginning, that when you run reinforcement learning agents, it almost feels like you are developing some intelligence within your computer and you're actually building an AI agent, because these rewards are increasing simply based on experience. I have not provided any kind of input output pairs of training data. In fact, you saw how the output or the target is calculated from the neural network itself, but using the next states and observations. So slowly the rewards start to increase, and this graph is an indication that everything is working fine. So here you can see how the epsilon decay progresses. Initially, we use a very high epsilon, you move around randomly, and then as the model starts getting better and better, you start to exploit more and explore less. So this is it. It looks very nice that the rewards is increasing and it's winning around 20 to 21 games, which is quite good, which is excellent actually. And we see. So this is the training process has started. It will take some time for all of you to complete this process. Now I want to show you the results that I obtained for this. Now to get the videos, you have to run this second script, which is dqn underscore play.py. Once you finish the training, you have to run this script so that all the videos will be saved in this local folder itself. And then this is what you get. Let me show you. Yeah, so initially, when you just stop the training midway and see what the agent does, you see something like this. You see my agent is the one in green, and it simply sits at the bottom of the screen. It does not do anything because it can't understand what to do. So very bad. But then afterwards, after the training is completed, when your rewards slowly start to increase, this is how my agent plays. So initially it loses one or two rounds, and then it really starts to learn how to get the ball past the opponent, and it follows a specific strategy to win. So this is the first time you see this locally run on your machine. It's extremely satisfying to see that only through experience you are able to build a reinforcement learning agent which learns through experience and which can play games like these, which is amazing to see. Remember, we had no experience. We did not know the model, the transition probabilities. We did not know anything. The only thing we used was the Bellman equation was fundamental to develop our neural network. So you can see it gets a score of around 20. That's why we get those rewards around 20 to 21. Okay, so this is what you are expected to see towards the end when you run the code. And I just want to show you the final flow so that you understand what's going on. Okay, so this is the final flow of the entire process, right? So initially we play the game a lot of times and update the replay buffer. So you can see that every experience in the replay buffer, it consists of the current state and the next state, basically S, A, R, and S dash. And like that, we have a lot of experiences. Now, out of this, we randomly sample 32 experiences so that the correlation is broken. And we pass these 32 experiences as the input. Uh, we convert this to pixels, pass it as an input to the neural network. And then at the bottom, we have this target neural network already in place, right? So then we run a gradient descent algorithm to train our neural network for 1,000 time steps. Till that time, these weights are frozen. After 1,000 time steps, there is a sync between this neural network and the target network. So these weights also get updated. And then what we do is, after the neural network is trained, we again sample from the new sample the actions from or use the neural network to predict the actions for a specific set of observations and then interact with the environment and generate more experiences. This is very important because if you do not have this loop, your replay buffer will have experiences which are not optimal. But as our network gets better and better, we need to store observations and actions which correspond to our neural network learning from experiences. So this is why this loop is complete, that after this neural network is trained, we again update this experience buffer. And then this entire loop goes on. We sample from experiences, train the neural network, froze the target network, transfer weights to the target network, then update the replay buffer by utilizing the neural network to take actions within the environment, and then keep on doing this till the time that these replay buffer gets filled with experiences which are optimal, and then you don't have much to train with. So this is the entire workflow of deep Q networks, and this is exactly what Google DeepMind did when they introduced Atari, and or they showed how games of Atari can be played using neural networks, or using deep neural networks. That's why the name DQN was born. So you might see the name DQN in a lot of places, and this was the birth of deep reinforcement learning, in my opinion. So now I have just showed you one single environment and how you can run the code in that environment, which is the Pong environment. But within Atari suite, there are a lot of different games like Space Invaders. Then there are multiple other games. There are 20-30 games. So using this same framework, there is Sequest also. Using this same framework, you can train all those different games, but the computational time might vary. So the game of Pong, I specifically like because it uses uh, not a lot of computational resources, but at the same time it's very efficient to train, and within 7 hours we get the results on our computer. So I want all of you to run this training process, and to get the satisfaction for yourself with respect to how exactly this works, and how the training process works, and how can we train an agent to actually play video games. Okay, so this brings me to the end of the lecture today. Uh, as an homework, you can try out with the different environments to see how the agent works in different environments. But essentially, the workflow will stay exactly the same in uh, all these different environments and all the different cases. And now in the next lecture, we are going to cover a very important topics of policy gradients, which is at the heart of uh, RLHF, and also how modern RL algorithms like TRPO, PPO, GRPO work. So next lecture is also going to be extremely crucial. But in this lecture, I want you to just appreciate the value of Bellman equations, because I think that is really at the heart of this entire deep Q networks. Even though we have used neural networks and all that, we would have been nowhere without Bellman equations. So that is very important to understand. Okay, everyone. Just one last point which I want to highlight. Some of you might be wondering how exactly is this working, having this target network and input network. What is the intuition behind that? So the intuition, how exactly our agent improves is that, let's say you play a game of Pong and your environment uh, gives a positive reward. Okay, so what will happen is, because you get a positive reward, that positive reward will be reflected uh, in the uh, in the target value, because you have r plus gamma times q dash. So when you let's say accidentally make a move which gets you a positive reward, it will be reflected in this target, and your q values will try to match that target. So your weight parameters will be updated in such a way that the state at which you get a high reward, its previous state the Q value of its previous state will be increased. And then once that is increased, the Q values of the state before that will also increase. So it's like a reverse effect, the way I imagine. If you have a very good game, let's say I play a game of chess and I win. Now, I should not give credit only to the last move, right? But I should give credit to a series of moves which have happened before the last move. In the game of Pong, also something similar happens, and this happens because we have this target network which calculates Q value of the next state. So if this has a high value, the Q value of the previous state also increases because essentially you're trying to reduce this loss between these two networks. And then that propagates backwards so that your Q values then start to change in such a way that you are reinforcing your actions which are getting you positive rewards. So sometimes in this whole picture, the main intuition gets lost. So that has to be clear. So you can think about that as well. How exactly do we propagate backwards so that not just the last state gets the reward, but the states which have preceded to that are also important, right? In the game of Pong, I might get my ball past the opponent, so that's a high reward. But how my paddle moved before, that is very important, and all those states and actions should get high rewards because those movements were finally critical for me to win that round. So that is what happens in this whole process from a broader perspective. Okay, everyone. Thanks for attending, and I'll meet you next week. All the best. Bye.